All right, welcome everybody. Hope you're doing well. Let's go ahead and get started. We got a lot of material to cover today, so we're going to need all the time that we've got available. As you can see, I got a camera. No, you obviously see that, but I got a light. It's right next to my camera, so I'm not going to be like this backlit mystery anymore. Make another improvement to our lectures is that maybe the backlighting isn't so bad. I'll again invite you that if you have a webcam, I'd love to have you turn it on. It becomes less awkward for me to teach if you speak your questions rather than type them. And if you switch on your camera, I kind of feel like we're all in this together and I'm teaching to actual humans rather than just icons. So all right, so let's go over some announcements here and get into the material. The introductory assignment is that opportunity for 10 bonus points on the homework grade. It concludes today at 5 p.m. And I don't have official office hours today, but you're welcome to try and call me. I've got an appointment with another faculty member at 12:30, and I've got lab at 2 and at 3 today, fluids lab. But I'm going to be in and out of the office and I'll pick up when I can. So if you haven't already called me for that introductory assignment, please do. Then your first calculation-based homework assignment is due before class on Thursday of this week. So you've got 48 hours remaining to finalize that assignment. We're going to cover some information today that I hope will further address the last question on that homework assignment. So any questions on the announcements before we start talking about gas laws? Any questions at all?
Switching who comes to the lab today at what time?
If you were at the lab at 2 o'clock last week, that means that you should come at 3 o'clock this week, and vice versa. If you came to lab at 3 o'clock last week, then that means come at 2 this week. And the lab handout is available now on Blackboard. I am going to print out a copy for you to have in the lab, so you don't need to print one if you don't want to. Are there other questions related to the announcements?
Dr. Waite, for the lab report, do you want that on like Microsoft Word, or how do you want that submitted?
Are you talking about the report for last week?
Yeah, like the one that's like Lab 0 or whatever about the safety.
Yeah. There's no particular format that you need to follow for that. Just, for that one you're addressing 5 lab hazards and how to prevent them, and so you can do it PDF, it can be Word, you can type directly into the Blackboard and submit it that way. I don't have any preference. All right, so this is where we left off last time. We were going to start to talk about the gas laws and how they apply to our calculations in fluid mechanics. You probably remember from chemistry the universal ideal gas law, PV equals nRT. And so in the ideal gas law, P is pressure, and it's the absolute pressure, meaning the pressure measured above a vacuum. V is the volume occupied by a certain amount of gas. And how much gas are we talking about is the first term on the right side of the equation. N refers to the number of moles of gas. And you probably remember that a mole of gas is 6.02 times 10 to the 23rd number of particles. And so if the gas is pure oxygen, then that would mean it's a mole of gas is 6 times 10 to the 23rd molecules of oxygen. U is the universal gas constant, and it tells you the ratio between the amount of gas in terms of its temperature and the number of particles, and then the product of the volume and the pressure. And so it's a proportionality factor that we'll take a look at some of the various units that we can use for that. Whenever doing the ideal gas laws, T, temperature, is going to be expressed in absolute terms. And so if we're in SI units, then that would be Kelvin. Now, at the lower part of the screen, we're going to go through just an algebraic rearrangement to illustrate how we can use the ideal gas law in a convenient way to find out the density of a gas and also the weight of gas the weight of a certain amount of gas. And just starting with this term on the left, standard gas law, PV equals nRT. And by the way, the R that I've added here has this subscript U, and that means it's the universal gas law constant. You can derive a gas law constant that is specific to a particular gas, but this universal gas constant applies to all gases. And we'll get into the difference between the two in just a moment. But just to be completely explicit here, we're talking about the universal gas law. Now we, as you can see, moved the volume term to the right-hand side of the equation, and so that leaves us with the pressure of the gas on the left. So what we're saying is this is the pressure that the gas is going to exist at when we have a certain number of moles, so it's a certain number of particles of gas at a certain temperature crammed inside a given volume, and then this proportionality factor R. So P is going to be the pressure that gas exists when we have a certain number of particles, and the temperature term just is really a reflection of the kinetic energy of the particles. And so that the warmer the temperature of the gas particles are, the more that they're going to be bouncing around, and of course that's going to increase the pressure, because as they have more kinetic energy and there's more collisions and more activity of the gas, then it would have a tendency to exert more pressure on a given volume, or expand if we were keeping the pressure constant. So this final term, what we're doing is we're multiplying both the numerator and the denominator by the molecular weight for a particular gas. And by the molecular weight, we're talking about how many grams of a certain gas is required for there to be a mole of it. And so for instance, oxygen gas, O2, has a molecular weight of 32 grams per mole. And so when we have this term of molecular weight multiplied by the number of moles, then think about what we're going to result in the numerator. The N, the number of moles, multiplied by grams per mole. And so that's going to tell you essentially the mass in the numerator, and then the R and the U term are going to convert over to the gas law constant that is for a particular gas. And so the reason why we are multiplying both the numerator and the denominator by the molecular weight is that in the numerator it's going to turn into the amount of gas that's present, and then that turns us from the universal gas law constant into the gas constant that's specific to the gas in question. So the usable form of this equation that we're going to be really applying is the pressure will be determined by the density of the gas constant R, that's not the same as R sub U. The R is for whatever that gas is, whether it be oxygen or helium or hydrogen, and then the temperature still in absolute terms. So just to get some practice with that equation, let's take a look at this example where we have a room, and it's a rectangularly shaped room with the dimensions 4 meters by 5 by 6. And what we know is the pressure of the gas in that room, 100 kilopascals. That's very close to our typical atmospheric pressure. The typical standard pressure at sea level is 101.3 kilopascals. So this would be the typical pressure just slightly above sea level. And 25 Celsius is a pretty typical temperature, maybe a little bit warmer than how the temperature in your home, but not way off the charts. And so what we want to do is we want to find out for air. Air, of course, is a mixture of gases. It's a mixture of mostly nitrogen, a big portion of oxygen, and then trace amounts of other gases like helium, hydrogen, carbon dioxide, and so on. So the R value for that mixture of gas is given here, 287. That's the R value that's specific to air. So let's go through the three things we want to know in this example is the gas's density. And so here's the formula for determining the density. The specific gravity, now SG is a term that was defined last week, and I'm not going to tell you again what that is, not right now. I will, of course, when we go over the solution together, but I want to see if you remember what specific gravity is. And then finally, the mass of air in the room. So if we know the room's volume, which we can calculate, if you know the room's the density of the gas in the room, then you should be able to find out the mass of air in the room. Now these units, joules per kilogram Kelvin, that is going to be the units that you can substitute directly into T, but there's so many different units for gas law constants. As you can see, I took this from a table that's available online. Because we can measure volume in liters or cubic meters or centimeters cubed, because we can measure volume in terms of cubic feet, because we measure pressure in either pounds of force or PSI or bar or atmosphere, every combination of these different units yields a different gas law constant. And so I just wanted to show you why it is in this list of all of the options, why do we choose 287 joules per kilogram Kelvin. So before I turn you loose to try some of these calculations, I just wanted to show you, if we expand out the units of 287 joules per kilogram Kelvin, what does that actually mean? Well, let me make this a little, oh no, I don't want you to see the answer yet. Alright. Alright, so looking at the units, 287 joules per kilogram Kelvin. A joule expands out to a Newton meter. And so a Newton of force exerted over a meter of distance is a joule. And we can further break down a Newton into its components. A Newton is a kilogram meter per second squared. And so you can see that here where it's N, I've expanded that out to kilogram meter per second squared. All right, and then this meter is from the previous step, and the kilogram and the Kelvin is carried over from the previous. And so when we cancel out all the common units, then the units of joule kilogram Kelvin actually is meter squared divided by second squared times Kelvin. So this substituted into the formula that we're going to be applying. So if we use those units and substitute it in here, then you're going to see that you end up with kilograms per cubic meter. So if you've printed off the notes, for now, just write down meter squared divided by second squared times Kelvin. So write down these units, and then you'll see how it all cancels out. All right, so I'm going to pause for a moment so that you can calculate these three things: the density of the air at these conditions, the specific gravity, and hopefully you remember what we mean by specific gravity, and then finally, what's the mass of air in the room. In with the correct answer to the density. So let's see if we all agree what we should do to calculate the density with that formula. Oh God, that's too much. Alright, so here's the formula that we're substituting into. Density is pressure divided by the R for that particular gas multiplied by temperature in absolute terms. How do we know to use Kelvin? Well, because we're going to be multiplying it by this R value that has Kelvin units of temperature. So if we left it as Celsius, it wouldn't cancel out. That's why it's a good thing to always write the units as you're doing your calculations. So here on the screen you can see that we've got the pressure is 100,000. Now 100,000 newtons per meter squared is the same thing as, if you expand out, a newton is a kilogram meter per second squared. So then that makes 100,000 newtons per meter squared. It's the same as 100,000 kilograms divided by second squared times meters. And then we have the R values. that previously were kind of detailed how we got the units from that. And so when everything cancels out, we're going to be left with kilograms per cubic meter. And so the density is 1.169 kilograms per cubic meter. And if you open up your book, your textbook has, let me grab the book. All right, so here's the textbook, and in Appendix A at the back of the book, it has the fluid properties. So here in Appendix A, it's got a bunch of properties for ideal gases, for air, for typical temp 15 degrees Celsius and 1 atmosphere. It tells us the density of air is 1.22 kilograms per cubic meter. And so that's at a slightly different temperature. You know, in the book, it's saying that's the temperature for 15 Celsius, and this example is at 25 Celsius. And so the density will vary slightly because of the different conditions. But, you know, it's always good to do like a ballpark check to make sure that things are matching up the way you'd expect. All right, so that is the density. Now, specific gravity. Do you remember what the definition of specific gravity is? Let's go back to the slide where that idea was introduced, just in case it has slipped your mind. Specific gravity is the ratio of the density of a fluid to the density of water. And Benjamin has correctly identified that what we're going to do is we're going to take the density, which we already determined, and we're going to divide it by the density of water. So we take the 1.169 kilograms and divide that by 1,000 kilograms per cubic meter. So here is the specific gravity. So it's 0.001169, or in other words, 1.169 times 10 to the minus third. So that's specific gravity. And then finally, mass. How do we find the mass with density and volume? Mass is volume times density. So look at the units there. If we have the volume in cubic meters and multiply it by density, that's going to leave kilograms in the end. So if you don't know the formula for mass equals volume times density, you can always derive formulas like that just simply by looking at the units. I mean, if you know the density of the fluid, you can figure out how you're going to find mass just by looking at what's in the numerator, what's in the denominator, and kind of just prove it to yourself. So it's 140.3 kilograms of air is the solution to that one. So any questions so far on this example?
See your conversion factor for your density that you used up top again.
Yep. So this has both how we took the joules per kilogram Kelvin to its base units. You know, the base units, that all other units are derived from length, time, and temperature. So here we have broken down the newtons into kilograms, you know, mass, length, time, temperature. So breaking it down to the base units there, and then the same thing with the pressure. All right, so let's now, after that first example, continue on and talk a little bit about pressure today. If you had a pound of water and you put it in a graduated cylinder like this, and let's say that the cross-sectional area of the cylinder is 1 square inch. You know, so to get it to be 1 square inch, you could calculate the diameter. You know, if area is 1 square inch and area is pi d squared divided by 4, then I guess that means the diameter is going to be less than an inch. the point is that the height of water, just based on the density of water and the amount of space that it occupies, a pound of water would rise to a height of 2.31 feet in a graduated cylinder that has a cross-sectional area of 1 square inch. And by cross-sectional area, what I mean is like the bottom of it, the circular area is 1 square inch. So sometimes when you are learning about units, it can be considered pretty typical to speak of pressure in an equivalent height of water. And so 1 psi, for example, a pound of water, which is on top of a square inch of area. So that's the definition of a pound per square inch. 1 psi is the mass, the force of the water above that area. So 1 pound of force above an inch squared. Head is just an interesting term that's used to describe how high above a certain location the water rises. So head and pressure are sometimes used interchangeably, but I just wanted to introduce that idea that when we talk about pressure, it really does mean an amount of water above the surface, or it can be a gas as well. All right. Now here is a Tesla. It's a very expensive car that I'll never own, but I can sure appreciate the beauty of it. And let's talk about the least interesting aspect of the Tesla. The very least interesting thing is probably the tires. But it's a useful illustration for what we need to discuss today, these tires. If you have a car, you may have noticed that in the door jamb, sometimes it's on the door, sometimes it's the space that the door presses up against. There's this specifications plate that tells you the pressure that the tire should be inflated to. And so on this particular car, you can see that it's suggesting that the tire should be inflated to 45 psi, or 310 kilopascals. And that's the pressure for both the front tires and the rear tires. Sometimes it's different. But in this case, they're saying, if you have one of these pressure gauges and you go to a gas station that has a compressor, you should fill up the tires until the gauge is reading 45 psi. So that's simple enough. But what if you were measuring the pressure of tires on the moon rather than tires on Earth? Things would be a little bit different. So let's say this rover in particular, you can tell that the tires are inflated. But what if we took this rover back to Earth and we measured what is the tire pressure? Would we get the same measurement on the moon as we would on the Earth? Anyone want to guess that? Would you have the same pressure? No. Zach and Reagan both say no. Why is it that the pressure would be different? Gavin is saying it would be higher on Earth. I actually disagree. I think that the pressure gauge would measure higher in space. And the reason why is that when you're measuring the pressure here on Earth, the tire pressure is measuring the difference between two things. This gauge is measuring the difference between the pressure in the tire and the pressure on the inside of the tire and the pressure of the outside of the tire. Because like right now on Earth, there is gas pressure surrounding us. And so on Earth, it's measuring the difference between atmospheric and the pressure inside the tire. And so in space, assuming that the temperature issue isn't the main reason, because it is colder in space, but let's assume that it's just about the difference in the pressure of the surrounding gases. Well, in space, there isn't an atmosphere. And so you're measuring the distance from vacuum to the pressure in the tires. And so there's a little illustration I'll show you in a moment, but we have to define some terms to really understand kind of how the different ways that we measure pressure. And sometimes we measure pressure on an absolute basis, meaning that we're using our reference point is no gas and no pressure. So the reference point is sometimes called a datum. It's a basis point for measurement. And absolute pressure is that you're using vacuum as the starting point. You're saying 0 is space. And in Huntington, my tires would read the absolute pressure of the atmosphere is 101 kilopascals, and so that's the atmospheric pressure. And so my tires are going to be, in absolute terms, they're going to be 335 kilopascals, because in absolute terms I would have to add the measured pressure to the atmospheric pressure. And so ABS, that subscript, means the absolute pressure of this thing that we're measuring. Gauge pressure, on the other hand, is when you are saying, let's make the datum, that reference point, be the atmosphere that surrounds us, rather than 0 pressure. And so, you know, the pressure gauge, this one, when it says 0, like if you were at Sheets right now, filling up your tires, if you had one of these things and it said 0, that doesn't actually mean that there's a vacuum inside your tires. It just means that it's the same pressure as the atmosphere. And so it's what is the 0 point. And in the case of gauge, we're just saying, let's assume that our 0 point is the atmosphere that surrounds us, and then we'll just measure pressure beyond that. So this illustration is saying, you know, what is your basis point? You know, what is the reference that you're going to be measuring all of the pressures from? Are you going to be saying you want to know how much is the pressure beyond atmospheric, or do you want to know how much pressure is there in your tires beyond vacuum? Now the distance between those two datums is 101 kilopascals, and so my tires, if I measure it from the atmosphere as the reference point, then that's the gauge pressure of 234 kilopascals. But if I'm measuring starting from the vacuum, meaning no molecules, no pressure, then the absolute pressure of my tires is 335. Zach asks, is absolute pressure actually irrelevant? It is when we're doing gas law calculations. Okay, so just to try out some more gas law calculations, let's say that we have a known volume of oxygen. It's a cylinder that has a volume of 2.5 cubic meters, and we pressurize it to known pressure, so that's 7650 kilopascals, and that's the absolute pressure. And the materials themselves have a mass of 50 kilograms, and then the temperature of the gas is 120 degrees Celsius. And we want to know what's the total weight of the gas and the tank together. And you can see in bold I've said weight. So we need to calculate the newtons, not just the kilograms there. So the steps here, what we're going to do first of all is find the temperature in Kelvin. You convert from Celsius to Kelvin, because you can see from this R value that the temperature units are going to be in Kelvin to cancel out. And same as before, joules per kilogram Kelvin is going to be what we can substitute directly into this equation, because the real units of joules per kilogram Kelvin is meter squared divided by second squared times Kelvin. So that'll be the correct units. But what we have to do is convert from kilopascals. When you put it into this formula for density, you need to convert from kilopascals to newtons per meter squared. 1 kilopascal means 1,000 pascals, and the pascal is the same thing as a newton per meter squared. So 7650 kilopascals is the same thing as 7,650,000 newtons per meter squared. Alright, so hopefully you've got your calculator handy. Calculate, number 1, the density of the oxygen, number 2, the mass of the oxygen, and then number 3, the weight of the tank and the oxygen together. Alright, let's look here at what is going on. Alright, the given data that we've got is the volume of the tank, the absolute pressure is known, the mass of the tank, the temperature, the R value, and that R value is the R value that's specific to this. What's the tank filled with? Does it just say it's air or is it oxygen? Alright, yeah, that's the R value for oxygen. Okay. And then you can see that I've converted the temperature over to Kelvin. So to calculate the density, we just substitute in the pressure, converting it from kilopascals into either pascals, and a pascal is the same thing as a Newton per meter squared. So 74.9 kilograms per cubic meter. Now, what we saw from a typical uncompressed pressure of gas was that the density was around like 1.2 kilograms per cubic meter. And so here, why is there such a higher density of the gas? Well, it's because this exists at a much greater pressure than the 101 kilopascals in the previous example. So you always want to kind of just do a sanity check, as they say, or like make sure that the numbers are qualitatively headed in the direction that you'd expect, and here they are. So we have the density of the oxygen, and now the next part of the problem, it asked us to determine the weight, meaning the force applied by the tank and the gas. So we need to find out the mass of oxygen that's there, and if we know the density, then we can calculate the mass of oxygen by multiplying the density that's known for the oxygen and the volume that oxygen occupies. And so you should calculate that the mass of the oxygen is 187.2 kilograms. And so then the combined mass of the tank and the oxygen together is 237 kilograms. And finally, converting that over into the weight, we have to multiply by G. Weight is mass times gravity. So weight is going to be 2327 newtons. All right. So that's another illustration of how these gas laws can be used to kind of interchangeably determine the mass or the pressure or the volume by making use of that gas constant. All right, let's change gears a little bit, and here's a picture from an old book that I used to use when I very first started teaching fluid mechanics, but the picture kind of still tells the same story that it did back then, even though it's in black and white. You can see what's going on, and maybe you've seen this firsthand with your own eyes before. What we're seeing in the picture is an insect that somehow is able to walk on water. So it's a bug that's walking on water, and how is it possible? Well, it's possible because that insect doesn't weigh very much, and it's also possible because it's spreading out its weight. If you look at its long legs that it has, it's distributing the weight over the surface there. So if its force was more concentrated, if it had shorter legs than this, then it would probably pierce downward through the fluid membrane, and it wouldn't be able to walk on top of the water like it is right now. In general, what we can say, if we're doing a force balance, then we can say that the downward forces, meaning the gravity and the combined mass and gravity effect of this bug, is less than whatever is supporting it. And what's supporting it, the force that is resisting the downward forces, are something that we're going to call surface tension. And let's take a quick look at a little video clip that illustrates this same effect with a larger scale rather than a bug, it's actually a lizard that's able to do something similar. Oh, I didn't want to do that. I just closed my presentation and open it again. All right, so this surface tension effect, you can see it with bugs or lizards walking on water. You can see it with, you can see the picture here of a paper clip floating on top of the water. We're going to actually see that in the lab today and tomorrow. By the way, on the subject of the lab, there's, I don't know, about 10 mechanical engineering students in the class this semester. You're welcome to attend the lab. You're not enrolled in the lab because mechanical students don't take 319 any longer. They've got a combined lab with another course. But if you want to see the demonstrations and just kind of observe some of the phenomena that the civil engineering students are going to be seeing, you don't have to enroll in the course. You can just show up for the lab and participate in the experiments and turn in a report if you want to. Don't turn in a report. It's entirely up to you. But I just wanted to put the offer out there that if you want to see, for example, today's demonstration, which is a paper clip floating on top of a water. Jeremy asks the room and time. It's in room 1228 at 2 and 3 o'clock on Tuesdays and Wednesdays. So today and tomorrow, you could come at 2 or come at 3. And it's 1228 down on the ground floor of this engineering building. Okay, so surface tension arises out of intermolecular forces. It's when water is attracted to itself. And we know that water is a polar molecule and it's relatively negatively charged on the oxygen and relatively positive charged on the hydrogen. And so it has a, one water molecule will be weakly attracted to adjacent water molecules. And that causes a surface tension because at the top of the water, the attractive force that the water molecules are experiencing are distributed over a smaller number of adjacent molecules. Just as an illustration, below the surface, this molecule that's below the surface, it's interacting with all of the adjacent molecules, the one that's to the left and to the right and above and below. But up at the surface, there are relatively fewer molecules for this water molecule to interact with because there's none that are above it. And so there's a higher forces of attraction at the top, at the surface, simply because when you've got the layer of the air on top, then all of the attraction that would have been with the molecule above it is instead exerted to the molecules that are to the side. And so there is kind of a membrane effect at the top. And different liquids are attracted at different amounts. And the constant that allows us to characterize the strength of that attractive bond is called surface tension. And so sigma has units of newtons per meter, and you can see that for water it varies as a function of temperature. And at 20 degrees Celsius it's 0.073 newtons per meter. As you get warmer, that force is weaker. But what we'll look at today in the lab is comparing the surface tension of water and the surface tension of oil. And so for example, SAE 30 oil has a surface tension of 0.035, which means that oil molecules aren't as attracted to one another as water molecules. And so we would expect that surface layer is going to be weaker than it is for water. You can calculate the magnitude of the force and even determine how much of a weight can be supported by this membrane effect at the top. the formula that allows you to calculate the surface tension force is shown here on the screen. You'd multiply the surface tension constant by a length. And it's the length over which the surface tension is acting. And there's a trick to that we'll take a look at with some examples. But one of the ways that you apply the capillary effect is if you dip a glass tube down into water, it will cause the water to rise in the glass tube. And this is another thing that we'll observe in the lab today. I have a small diameter glass tube, and when we dip the tube into a cup of water, the water will rise up inside of the tube because the water is attracted not only to itself, but the water is also attracted to the glass, the molecules in the glass. Glass is made out of silicon dioxide, which is also able to have an attractive force exerted on the water. And so the water will rise up a certain height, delta H. And how much it rises up depends on the diameter of the tube. And if you have a large diameter tube, then there's hardly going to be any measurable capillary rise. But as the diameter of the tube gets smaller, then the delta H gets increasingly higher and higher. And the reason for that is that the surface tension force is pulling the water up. And what's causing the water to be in equilibrium, the reason something that's dragging it down, is the weight of the water. And so here L, the length parameter that determines the magnitude of the surface tension, in the case of a circular glass tube like this, it's the circumference that the water is in contact with the glass tube. And so, circumference is pi d. So pi times the diameter would tell you the circumference. And so you can find the force, the surface tension force, by multiplying the length parameter by the sigma, the fluid property for whatever the fluid is. There's also something that we have to consider called the contact angle, and the contact angle or the wetting angle varies depending on what the fluid is. For water, which is what we're going to be using, the contact angle is essentially 0 degrees. But if you were going to put, for example, mercury in a glass tube like this, the contact angle would not be 0, and you'd measure that the contact of the water with the glass tube in the edge, there would be a little bit of an observable angle there at the meniscus. So here's the formula that will allow us to determine how high the water is going to rise in a capillary tube. The surface tension force is the applicable distance, which is pi d, multiplied by sigma, which is the fluid constant. And then cosine of the angle is kind of the general formula, but if the angle is 0, like it is for water, then the cosine of 0 just becomes 1. So really the formula is pi d times sigma for water. And that tells you how much of a force is drawing the water up. That's why it rises in the capillary tube. But then the weight of the water is acting downward. And so how you would calculate the weight of the water that's inside that capillary tube is it's going to be the volume of water multiplied by the unit weight, gamma. And of course the volume of water, if this is a circular tube, then the shape of the water inside of there is the shape of a cylinder. And so the volume would be the cross-sectional area multiplied by delta H. So you find delta H, you find how high the water is rising in this capillary tube by doing a force balance. Let's try that out. Let's calculate how high the water is going to rise in the glass tube if the inside diameter is 1.6 millimeters, and if it's at 20 degrees Celsius, then here is the sigma that we use for water. And when it's in equilibrium, that means that the weight of the water acting downward is it's the same magnitude as the force that's drawing the water upward. Because at first, when we very first dip this glass tube into the water, it won't be in equilibrium. The water will quickly rise and then it will stop rising when the weight of the water inside the tube is equal to the surface tension force. Alright, so to solve this, if I go back to the previous formula, so write this in the margin of your notes. The force is going to be, the force due to surface tension is sigma pi d. And so for this example, on the left-hand side is sigma pi d, and the right-hand side, the weight of the water, is going to be the volume of the water multiplied by gamma. And so by the volume, what we mean is just the volume that's above the water line. So think about the shape of the water element that's above the water line. It's going to be cylindrical in shape, and so its volume is going to be delta H, which is an unknown variable, multiplied by the area, and the area is defined by this diameter. The cross-sectional area we can get from the diameter. Pi d squared divided by 4 is area. So it's an equilibrium. Let me just give you kind of the initial hints, and then you can do the substitutions and the calculations if you haven't already started. Let me just kind of show you how to do the initial setup of this one. Alright, so we start with the given details. It's like I've never clicked on a screen before. Gavin, you are off by a factor of 10, but I think you're headed in the right direction. Okay, so here's the gamma of the fluid at 20 degrees Celsius, the unit weight of water, 9790 newtons per meter cubed. The surface tension of water at that temperature, and then if we convert the diameter from millimeters to meters, it's 1.6 times 10 to the minus 3 meters. Okay, so we're going to say that there's an equilibrium between the surface tension force, F sub s, and the weight of the water, which is acting downward. So here I've done a little sketch, and I've kind of identified we've got a diameter of the capillary tube, some unknown delta H that the water is going to rise to, and then the force acting down is the weight of the water, and what's drawing it up above the surrounding water line is the surface tension force. So like, why is the water rising? It's because it wants to get in contact with that glass tube. It wants to maximize the physical area of contact with the glass tube. So the weight of the water we can calculate as volume times gamma, and then the surface tension is going to be sigma times pi d cosine theta, where cosine in this case for water is 0. So equilibrium means set these two equations equal to each other. The equation for the weight of the water on the right hand side, the surface tension on the left hand side, and the only variable that we don't have a number for is delta H. So set this equation equal to this equation, set them equal, substitute in all the values that we know, and the only unknown will be delta H, and that's what we're solving for, is what's the height that the water level is going to rise to. So you can see that if you rearrange this expression to solve for the unknown delta H, so I have my equation for surface tension force. I have my equation for the weight of the water. Set them equal, and then rearrange to solve for delta H. So when things cancel out, canceling out common terms, I'm going to have 4 times sigma multiplied by cosine of theta divided by d times gamma. And so we can substitute in all of the values that we know. The surface tension constant for water at 20 Celsius, 0.073 newtons per meter. The water contact angle between water and glass is 0 degrees, so cosine of 0. The diameter of this glass tube, 1.6 times 10 to the minus third meters, and then the unit weight of water, and so that's the 9790 newtons per meter cubed. And so that gives us a distance of 0.0186 meters, and expressed in millimeters, because that's kind of small, it maybe doesn't seem like much, but the water is going to rise up to a height of 18.6 millimeters inside the glass tube. So if you make the tube an even smaller diameter, then it would raise even higher. And the reason why is that when you make the diameter, let's say you cut the diameter in half. Well, if you cut the diameter in half, then you are going to be reducing the surface tension force, but you're going to be reducing the weight of the water even more dramatically. Because if you look at this formula, the surface tension force is a function of diameter, but the weight of the water is a function of diameter squared. So if you have half as much diameter, then you'll have half as much surface tension force, but you'd have 1/4 the weight of the water. So a really small diameter glass tube, the water could rise pretty dramatically. And you may think that, well, this is maybe kind of an obscure thing to be talking about, small diameter glass tubes. But this turns out to be really important in the natural world, because soil and sand behave very similarly to a small diameter glass tube. And so you know that there's water underground, aquifers, and water will rise up through the soil using this capillary effect above the actual saturated zone. There's an increased water content in the zone of aeration because of the capillary effect. So this has some real-world applications, and it's an important concept to be able to understand capillary rise. Let's just take a quick look at the homework assignment, because I want to point out, I think one of the problems, maybe two of these problems, has to do with surface tension and capillary effects. And so the first problem that's related to this says, to what height will water rise in a circular glass tube with an inside diameter of 0.1 millimeters? Okay, well that's going to be pretty easy now that you've done an example that was nearly the same. Problem 9, though, is a related problem. Even though it doesn't seem like it's related, it is closely related to what we've just been talking about. So in this problem, it's going to be a paper clip that is floating on top of the water. And from the segment lengths and the density, you'll be able to find out the weight of the paper clip. I'm asking here the maximum diameter of wire that's allowable for it to float. Because if it's a really small diameter wire, you know, just like a tiny little thread of wire, then it can float on the water, you know, no question, it's kind of obvious. But as the diameter gets bigger and bigger and bigger, it may not be able to float. And in the lab, we've got a paper clip that you have to be so careful to be able to get it to set on top of the water. And then we have smaller paper clips that set really easily on the water. So in this question, you're going to be putting into equilibrium the weight of the water and the surface tension forces. But the formula for surface tension, if we go back to the general formula for surface tension here, it's sigma pi d for a circular capillary tube, but here is the more general form of the surface tension formula. So this is the formula that you're going to use in question, was it 9? Yeah, question 9. You're setting two things in equilibrium, the weight of the paper clip and the surface tension of the water. So the surface tension constant, sigma, is easy enough. It just says to float on water. They don't tell you any particular temperature, so just consider the typical 0.073 newtons per meter, like we did in the example. But now what about the length parameter? You know, they're asking here to find the surface tension, you have to know the length. Now here's the key. Here's the big hint that I'm giving you. The length is going to be both sides. It's the left and the right side of the paper clip. So the paper clip interrupts the water in two different locations. And so the length is going to be the physical segment length that's described here. So for example, this segment of the paper clip where it says 23 millimeters, that's the physical length of the paper clip, but it actually interrupts the since it's on the left and the right of it that it's bending the water, it has a combined length of 46. And Gavin is asking about buoyancy, and no, on problem 9 we're going to be neglecting the buoyancy effect because it's going to be on top of the water rather than submerged in it. So we will neglect a buoyant effect, and it's only the surface tension force and equilibrium with the weight of the water. But the key that I want to emphasize is that in this case the effective length of the paper clip is double its physical length. So it's 2 times the length that's described here because it's bending the water on the left and on the right of the paper clip. All right. So we'll start talking about pressure now. You know what? Before we move further, I want to sketch something. I don't usually bother with this. Let's see. Okay, I think you see a blank whiteboard right now. So the paper clip, let's say if we unraveled the paper clip and it's just a straight wire. Here's the paper clip. It's circular. And here's the water. The water is on one side and it's being bent by the paper clip like that. So, you know, like if the paper clip has a certain length and it goes off in this direction, okay, then because it's bending the water in 2 locations, if this paper clip was like 10 centimeters, then the L we'd use would be 10 centimeters here that it bent the water and 10 centimeters there that it bent the water. So the L that you use in the surface tension equation is double the physical length. I hope that emphasizes it. Any questions about that before we move on?
So around the curve, it gives us the radiuses. The radiuses can be minimally different on the outside and the inside when we do that.
That's true.
How do you handle that?
Well, you're absolutely right. It is going to be a little bit different. I think what you should do is just neglect the fact that they're different. So with the radius, you can calculate the length of the segment. Just assume that the inside and the outside length is the same. Neglect that slight difference. Yeah.
Perfect.
All right. Other questions? All right. Let me share my screen again. Okay, pressure intensity is the magnitude of force exerted over an area, and a Pascal is a Newton of force exerted over a square meter of area. And it's a scalar, which means that the pressure has only magnitude. It's equal in all directions. So that if you go down into the ocean and you turn your ears from side to side, it's not like you can avoid the pressure by pointing your face down at the pool or pointing your face upward. No matter what direction your ears are oriented, you're going to feel and experience the same pressure regardless of your orientation. So it has magnitude but not direction. And compare these two different lakes, a narrow lake and a wide lake. You might think that the lake on the right is going to have more pressure at the bottom. But in both of these cases, the pressure is the same at the bottom of the lake. It doesn't depend on how wide it is. The pressure only depends on how deep it is. And so, there are some places where people will go scuba diving, like in a very narrow but very deep kind of a pool. And it doesn't matter how wide the pool is, it only matters how deep the pool is to experience the pressure. So when we get together in class on Thursday, what we're going to talk about is the formulas that we use to calculate pressure. And you've already got the sneak peek at that from our first lecture when we talked about Challenger Deep. But we'll continue talking more about pressure units in the lecture on Thursday. So just to summarize, again, the invitation is open for the mechanical engineers who'd care to observe our experiments that occur Tuesday at 2 and 3 and Wednesday at 2 or 3. But the thing that you have on your plate right now is the team assignment. If you want to get the extra points for contacting me on Teams, remember that what you do is just place the Teams call to me, and then when it's finished, you type in the time and the date that you did it into the assignment and then submit the assignment. And that way it'll open up the location into the gradebook where I can give you the points. And then the other homework assignment is due before class on Thursday. So if you have questions as you're working on it, you can try contacting me on Teams. And even if it's outside of my office hours, I'll try to pick up if I'm not busy with something else or in another meeting. Of course, you can send me an email, and I'll do my best to respond there. But otherwise, I'll see you on Thursday. That's all for today, unless I see you in the lab. But hope you have a good one. Take care.